The landscape at the Langley CIA complex includes several unique items which are part of Kryptos. Near the main entrance, a copper plate containing Morse code is sandwiched between slabs of granite. Across the sidewalk are more slabs of granite, on top of which is a compass engraved into the stone. The compass points across the slab to a lodestone which sits on top of yet another copper plate. Next, a smaller triangular piece of granite appears to pierce the surface of the ground. Within the courtyard, more slabs of rock flank two sides of a still pool of water. Behind this building is the focal point of the Kryptos installation, which includes letters carved into a copper sheet, petrified wood, another pool, and several large stones. A computer-generated model of the courtyard, which contains the main parts of Kryptos, allows for a dynamic view of the sculpture. Manipulating the S-shaped copper sheet into a flattened representation offers a more practical view. The copper sheet is actually composed of 4 panels, each of which are about 5 feet tall by about 9 feet wide. Panels 3 and 4 are reversed relative to panels 1 and 2. After the 2 panels are rotated, all of the letters are moved onto a grid, in preparation of attempting to solve the puzzle. The objects in these photos may hold clues for solving the puzzle on the copper sheet. But then again, they might not. Mr. Sanborn, in an interview with Wired News, was asked this question.
So just by reading the text taken from Kryptos and posted online, you can solve the puzzle?
To which Sanborn replied,
"Well, yeah.
The text of Kryptos appears to have been designed with a fictitious operative in the field in mind." Ed Scheidt, the man who taught cryptography to Jim Sanborn, described the idea of getting a message to an operative, and that the message must contain the clues or keys for decrypting the message. What might an operative who is trained in cryptography make of the text from the Kryptos panels? Scanning the characters of each line would reveal that there are 4 question marks breaking up the text. A trained eye would easily recognize the Vigenère tableau. The operative might find it curious that 3 alphabets surround the tableau, and that 4 extra columns have been appended to the right edge. At least some of the message was encrypted using substitution, because of the Vigenère tableau. However, the operative would likely perform a frequency analysis to expose any use of transposition. Many of the letters, J, K, Q, V, X and C, will show up in substitution, but only a few of these letters will exist in a message encrypted using transposition. An analysis of each line reveals that there is 1 section encrypted using transposition and 2 sections using substitution. The substitution sections were likely encrypted using the provided Vigenère tableau. Encrypting with a Vigenère tableau implies the use of 1 or more keywords. Keywords can often be recovered through an analysis of the cipher text. First, the operative would attempt to identify the length of the keyword by looking for sets of repeating letters in the cipher text. The first 2 lines contain the 5 repeating letters, VJYQT, at 20 characters apart. This suggests a keyword length of at least 5, so either 5 or 10. The next 2 lines contain the 5 repeating letters, GWHKK, at 16 characters apart. Therefore, the length of the keyword must be 5 or more letters, so it's most likely an 8-letter keyword. At lines 11 and 13, the letters NUVPD repeat at 72 characters. Possible keyword lengths are 6, 8, 9 and 12. The spacing of other pairs of repeated letters suggests a keyword length of 8. Because a longer message is easier to decrypt than a shorter one, the operative might attack the lines 3 through 14 first. To begin, the letters are placed into rows of 8, leaving out the punctuation. The two alphabets written at the top of this grid paper are for reference. The first is the Kryptos alphabet, taken from the first row of the Vigenère tableau. Below the letters are written the numbers 0 through 25. The second is just the regular alphabet. Below this alphabet are numbers from the logarithmic weights of letter probabilities in Chapter 9 of the 1990 Army Field Manual on Basic Cryptanalysis. These numbers were assigned to each letter based on how often the letter appears in the English language. To begin the analysis, the first column of ciphertext is written along the left side of the grid paper. The letter A is placed at the top of two columns to the right. Using the Vigenère tableau, each letter of the ciphertext is decrypted using the letter A as the key. The shorthand method is to subtract the key from the ciphertext. The numbers associated with each letter come from the first alphabet at the top of the grid paper. When the result is a negative number, 26 is added. Next, the plain text letters are each assigned a weight value from the logarithmic weights alphabet. These numbers are totaled at the bottom of the column. This entire process is repeated 25 more times using each letter of the alphabet as the key in the formula. Now, the column with the highest total will reveal the first letter of the 8-letter keyword. Here, column A has the highest total of 350, so the keyword likely begins with A. This entire process is repeated with each of the 8 columns of ciphertext. When finished, the keyword abscissa is revealed by the 8 columns which have the highest totals. The 8 columns with the highest totals contain the plain text which, when brought together, reveals the deciphered message. This process doesn't work as well when the amount of ciphertext is small, as is the case with the first 2 rows. As discovered earlier, the keyword length could be either 5 or 10, so the ciphertext is placed in rows of both 5 and 10 letters. Using the same process as before, the highest totals for the 5 columns results in a keyword of PELJK. The highest totals for the 10 columns results in a keyword of PALIZPEGJS. Because both keywords are non-English words, the plain text under both keywords is examined to see if any whole or partial English words stand out in any or all of the rows. The text under the 10-letter keyword looks the most promising. The word between is apparent in the first row. The 5th column should be replaced so that an E is at the top. An E at the top is found under the key letter M. The 7th column should be replaced so that an N is at the top. An N at the top is found under the key letter S. Now the keyword can be made out, and the rest of the ciphertext is easily decrypted. The portion of the ciphertext which involves the use of transposition will be addressed next. The simplest form of transposition is the rotation of a block of letters which have been arranged into a square. This method will be attempted first. The number of letters in the Kryptos transposition cipher will determine the size of the square to be used. The total is 336, and the square root of 336 is 18.33. An exact square is not possible. Therefore, several integer pairs are calculated which are close to 18.33, and are a factor of 336. These integer pairs are 12 and 28, 14 and 24, and 16 and 21. The number pair closest to forming an exact square is 16 and 21. The 336 letters are rotated and placed into rows of both 16 and 21 letters. Clockwise is the standard direction of rotation. One of these rectangles is selected to work with. A new rectangle is then started, bottom up, by taking 5 letters at a time, starting at the lower right corner of the chosen rectangle. If an English word doesn't start to form in the leftmost column, a new rectangle is started using 6 letters at a time, then 7, and so on. If not successful with the first selected rectangle, the other rectangle will be selected. Success is achieved when 12 letters at a time are taken from the 21 by 16 rectangle. The word "slowly" appears in the leftmost column, and more English words appear in other columns as well. Working from bottom to top, the remaining letters are placed into the rows of 12. The rectangle is rotated one last time, to make it easier to read. Here, the final result is placed into 12 rows of 28. The first encrypted message, referred to as K1, appears to make reference to the lower atmosphere, outer space, the northern lights, and the Earth's magnetic field. Between subtle shading and the absence of light lies the nuance of illusion. The word "illusion" contains the letter Q in place of the first L. The importance of this Q will be made apparent later in the recovery of keywords from the text of Kryptos. The second encrypted message, which is referred to as K2, is composed of several individual messages which are separated from each other by the letter X. The first message of K2 may be describing the act of hiding an entire ship from being detected by radar. The next 3 messages seem to share a common but vague topic. The word "underground", however, is misspelled. The extra letter U will play a part later in the recovery of keywords. The fifth message contains numbers in the form of latitude and longitude coordinates. These numbers will become important later as part of a proposed algorithm used in solving the fourth message. The sixth message, which appears to be part of the fifth message, simply says "ID by rows." However, Mr. Sanborn offered a correction, saying that a letter S had been omitted. The corrected message is preceded by an X, and says layer 2. This message will also play a part later in the recovery of keywords. The third encrypted message, which is referred to as K3, describes the act of opening the tomb of King Tutankhamun. The first line contains 3 raised letters, and the word "desperately", which is misspelled with an A in place of an E, and also has a missing E before the LY. All of these are clues in the recovery of keywords. The letter Q, just before the question mark at the end of K3, will also play a role later in the recovery of keywords from the text of Kryptos. The first part of this video was created in order to establish a mindset. This was done by demonstrating some of the standard analytical techniques involved in working with an encrypted message. The remainder of this video will focus on the final 97 letters of Kryptos referred to as K4. Since K4 appears to be a substitution cipher, keyword recovery would be attempted next. However, it becomes difficult when there are only short sets of repeating letters. K4 was designed to be more challenging. The keywords for K4 are actually hidden in the text of the sculpture. They must be found before K4 can be decrypted. After the keywords are found, there is a specific technique which was used in K4 to mask the English language, and that technique must be discovered as well. The next part of this video will cover an idea of what the keywords are, and where to find them, as well as present the masking technique which may have been used to arrange and encrypt those last 97 letters. First, the masking technique. K4 appears to have been encrypted by first placing the letters into rows below two keywords. For now, call the keywords A and B. Keyword A is 7 letters and keyword B is 11 letters, making a total of 18. K4 is placed into 5 rows of 18 and then 1 row of 7 below the two keywords. K4 is then divided on the keyword boundary, making 2 puzzles. At first glance, it appears that K4 was split, and each side was encrypted with its own keyword. The 2 sides were then put back together to appear as a single puzzle. Analysis of side A will produce valid results. So will analysis of side B. But, analysis on K4 as a single puzzle will fail. The English language won't be exposed, and we have uncovered the masking technique. If only it was that simple. It appears that the masking technique is more complicated than that. Encrypting requires the use of an alphabet, but with K4, it appears that each row segment, in each half of the puzzle, may have been encrypted with its own alphabet, or rather one of 6 possible alphabets. The 6 alphabets would be numbered 3 through 8, to match the same numbers used in the latitude and longitude coordinates provided in K2, which use only the numbers 3, 4, 5, 6, 7 and 8. The latitude coordinate numbers 3, 8, 5, 7, 6, 5, are placed alongside puzzle A, and the longitude coordinate numbers 7, 7, 8, 4, 4, are placed alongside puzzle B. The first row of puzzle A, for example, would be decrypted using alphabet number 3, the second row would use alphabet number 8, and so on. There may be even more to the masking technique than this. Instead of 2 keywords, there may be 11 keywords, 1 for each segment. Ed Scheidt made the comment that, the key is the algorithm, or the instructions of how to proceed. The keywords, A and B, give instructions to use 2 streams of letters as keywords. Instructions for where to get the streams of letters was not provided. However, the text of Kryptos would be a likely source for an operative in the field to find these key streams. Unlike an operative in the field, we have the advantage of seeing part of the original encryption sheets, which were supplied to the media by Mr. Sanborn. Using clues provided on this code sheet, it appears that the cipher text of K1 and K2 provide the 2 streams of letters. K4 has been arranged into rows of 18 letters, and on the code sheet can be seen marks at the 18th character on the first lines of both K1 and K2. 2 arrows are also drawn on K1, to show the direction in which the key stream is to be taken off, from left to right on the first row, and from right to left on the second row. Another mark, found on the second line of K1, indicates where to stop. 18 letters from K1 brings us to the first mark. 2 more sets of 18, and a set of 7 letters brings us to the stop mark, with a total of 61 letters from K1. "18 letters from K2 brings us to its mark. Then 18 more makes 36 letters from K2, and a total of 97 letters from the 2 streams. Another possibility is to take the 2 sets of 18 letters from K2, and place them before the letters from K1. Some trial and error will obviously be required to determine which arrangement is correct. The masking technique appears to have been accomplished by dividing K4 into 11 puzzles. using 2 key streams as 11 keywords, and 11 numbers as indices into 6 alphabets. If K4 was designed to be this complex, then it explains why Ed Scheidt said, you need to solve the technique first, and then go for the puzzle. As previously indicated, 6 alphabets are to be used. Where can they be found? The 6 alphabets are actually created from one alphabet, by using something called decimation. An alphabet is decimated when it is systematically reordered using a selected integer, such as 3. The third letter is taken first, then the 6th, 9th, 12th, and so on. When the end of the alphabet is reached, counting continues by wrapping around to the start. When all 26 letters have been taken, the alphabet has become a decimated alphabet. This doesn't work with some integers, such as 4. Every 4th letter is taken until the end of the alphabet is reached, then counting wraps around to the start. After the second loop, it wraps around to a letter which has already been taken. The only integers which can be used to decimate an alphabet must be coprime, with the length of the alphabet, which is 26 in this case. These integers are 1, 3, 5, 7, 9, 11, 15, 17, 19, 21, 23 and 25. What is needed are 6 alphabets decimated using the numbers 3, 4, 5, 6, 7 and 8. So, a 26-letter alphabet cannot be used. What can be used is a 31-letter alphabet, because 31 is a prime number, and all other integers are coprime with 31. This is why 4 extra columns were added to the Vigenère tableau. Each row now contains a 30-letter alphabet, and one of the rows has a 31-letter alphabet. The 6 required alphabets are obtained by decimating this alphabet using the numbers 3, 4, 5, 6, 7 and 8. Now for the recovery of keywords from the text of Kryptos. Up to now the 2 main keywords have been referred to as A and B. Together, they have the meaning of 2 key streams. Keyword A is the 7-letter word Lethean, which is a certain river in Greek mythology. Keyword B is the 11-letter word parasystole, which indicates the existence of a second pacemaker. Applying these words to cryptography, the role of a keyword is equated to being a pacemaker, with there being 2, and the river is equated to being a stream. Combined, there are 2 key streams. These 2 keywords have been hidden somewhere in the text of Kryptos. Not only did Mr. Sanborn have to figure out how to hide these 2 keywords, but he also had to figure a way to specify that they should be joined, end to end, and that the word Lethean should be placed before the word parasystole. The keyword parasystole is the easiest to discover. It is found in the plain text at the start of K3. The 2 words, slowly and desperately, possess most of the necessary letters in which to hide the word parasystole. 2 A's are needed, but there is only one A available, so an E was switched to an A. The W and the second L of the word slowly are not needed, as well as the D of desperately, so these 3 letters were raised as an indicator to get rid of them. All that is needed now is a way to communicate where to stop taking letters from the start of K3. Removing a letter would signal where to stop, so this is why the letter E was removed. The 3 raised letters, W, L and D, are replaced, after the transposition process has been completed, by the letters, Y, A and R. So, it's the position of the raised letters Y, A and R that's important, not the letters themselves. The keyword Lethean is much more difficult to recover from the text of Kryptos. The keyword palimpsest from K1 offers one of two clues. Palimpsest refers to layers of writing. The other clue can be found in the words, layer 2, located at the end of K2. If this top panel is layer 2, then the bottom panel must be layer 1. By placing one layer of this text on top of the other, a few of the same letters of both layers will become aligned. This is a type of steganography, and it is how the letters of the keyword Lithian were hidden in the text of Kryptos. Rather than showing how to find the keyword, it might be beneficial to see what steps were required to hide the keyword Lithian. To begin, the text was originally placed into rows of 31 characters, with 2 necessary exceptions. Also at this stage, the words illusion and underground are spelled correctly. The letter Q, placed at the end of K3, is intentional. It will act similar to a registration mark used by professional printers to align color layers. The ideal position for overlapping the 2 layers must be found next. By moving layer 2 9 rows down and 1 column to the right, 5 of the 7 letters of the keyword Lithian are either aligned or close to being aligned. The first letter is brought into alignment by shifting the corresponding row of layer 1 by 2 columns to the left. The 2 leftmost letters are then moved up and to the end of the row. The second letter is brought into alignment by shifting the corresponding row of layer 2 1 column to the left. The leftmost letter is also moved up and to the end of the next row. The fifth letter is brought into alignment by shifting the corresponding row of layer 2 1 column to the right. A letter is then borrowed from the end of the row above in order to fill the void at the left. An operative in the field will need to know how to align these 2 layers correctly. To mark this exact position, the letter Q on layer 1 is located, and then the letter directly beneath the Q on layer 2 is forced to become a Q when decrypted. It just happens to be the first L in the word illusion. Aligning the letter Q of both layers will bring 5 letters of the word Lithian into alignment. The remaining 2 letters of the word Lithian are to be aligned by first taking the top 9 rows of layer 1 and moving them down to cover the bottom 9 rows of layer 2. 2 letters are already aligned on the next row to be used. A letter T is wanted, but not the letter N. There happens to be another letter T which can be used. This letter T is brought into alignment by shifting the corresponding row of layer 2 1 column to the right. Doing so takes the letter N out of alignment. 1 letter is borrowed again from the end of the row above in order to fill the void at the left. Six of the 7 letters of the word Lithian have been aligned on both layers. The final required letter is an E. However, there happens to be 10 more letters which are already aligned just by coincidence. Assuming the final letter E is aligned, an instruction must be left to use only the first 7 letters to make a word. This is accomplished by finding the next available letter E on layer 1, and then forcing a misspelling of the word beneath it on layer 2. The desired effect will be to draw attention to the letter, and raise the question of why it is there. The answer, of course, is to take the letter E which is above the misspelled letter U, and unscramble the letters up to that point. One final task remains. An instruction must be included to place the word parasystole after the word Lithian. If one more random letter was brought into alignment, there would be 11 random letters after the 7 letters which make up the word Lithian. A letter E on each layer has a separation of only 1 column. These are brought into alignment by shifting the corresponding row of layer 1 1 column to the left. the leftmost letter is again moved up and to the end of the row. This brings the total to 11. However, to ensure additional words or phrases are not to be made from these random 11 letters, several letter swaps will be made. The row with the aligned letter C has 2 letters on each layer which are each separated by 2 columns. The row on layer 1 is shifted 1 column to the right, and a letter is borrowed from the end of the row above. The row on layer 2 is shifted 1 column to the left, and the leftmost letter is moved up and to the end of the row. The letter C is replaced by the letters A and N. Next, the letters H and S are both removed. They are on the same row, so they are tied to the same action. The row on layer 2 is shifted 1 column to the left, and the leftmost letter is moved up and to the end of the row. The removal of those 2 letters leaves 1 space to be filled. The next row contains the letter E, which is only off by 1 column between the 2 layers. The row on layer 1 is shifted 1 column to the right, and a letter is borrowed from the end of the row above. With the alignment of the letters completed, the rows are restored to their original positions. The jagged right edge of the 2 layers is explained by the adjustments which were made in order to align the 18 chosen letters. Imagine an operative in the field receiving only a sheet of paper with the transcribed text of Kryptos. The design of Kryptos was oriented toward a fictitious operative in the field. And the text of Kryptos contains both the message and the keys. Mr. Sanborn revealed that the text is the only item required for decrypting its messages. Half of the text contains encrypted messages. The other half contains a visionnaire tableau. Letter frequency analysis reveals the use of both substitution and transposition ciphers. Groups of repeating letters in the top half reveal that 2 keywords are used, and that the top half contains 2 puzzles. Keywords for the 2 puzzles are recovered by calculating the logarithmic weights assigned to all possible plain text letters for each puzzle. The columns with the highest totals reveal some or all of the keyword letters. The last question mark reveals the end of the 3rd puzzle, which utilizes a transposition cipher. It is decrypted by first rotating the 336 letters clockwise and into a block. This is followed by a restructuring of the block of letters to discover English text. Then one final rotation of the letters makes it readable. The solution to K4 comes in 2 stages, the first of which is to figure out how the puzzle was structured so that the English language will not be revealed through standard analysis techniques. The process begins by discovering 2 keywords in the text of Kryptos. One keyword is found at the start of the K3 plain text, by taking the letters up to the missing E, in the word desperately, and then discarding the 3 raised letters prior to unscrambling the remaining letters. The other keyword is found by first aligning the 2 cues on the bottom and top halves of the puzzle. 5 of the same letters will become aligned on the 2 layers. Bringing the top 9 rows down will reveal the alignment of 12 more letters. The letter E, which is on top of the letter U in the misspelled word underground, is also included. The first 7 letters are unscrambled to reveal the keyword Lithian. The remaining 11 letters are a placeholder for the keyword parasystole. The 97 letters of the fourth puzzle are then placed in rows below the two keywords. The puzzle is then divided on the keyword boundary, making a total of 11 row segments. Next, the 11 numbers provided in K2, as latitude and longitude coordinates, are placed alongside the 11 row segments. A specific alphabet in the center of the tableau, which is 31 letters in length, is decimated using the numbers 3 through 8, in order to make 6 unique alphabets. The integers which make up the coordinates, are used as indices into the list of 6 alphabets. The definitions of the two keywords Lithian and parasystole lead to the idea of using two key streams. The source of the key streams must be available to the operative in the field. The ciphertext of K1 and K2 offers streams of random letters as a source for the two key streams. The puzzle called K4 appears to actually be 11 puzzles, each encrypted as a one-time pad. This arrangement resembles the rows and divisions of the Berlin clock. The two words, Berlin and clock, are the solution to the 64th through the 74th letters of K4. The question now is, what algorithm was used to encrypt Berlin clock to NYP, VTT, MZFPK?